Hello. Today I will try to explain you practical work number one. This is called searching graphs, and in order to, you will have to uh, mm, make an algorithm for searching graphs. So in order to do this, we need to represent the graph. So the representations of the graph, the ways to represent are four. So the first one, it is incidence matrix, and here the rows correspond to vertices. Here A, B, C, D, E, and here we have the same thing, A, B, C, D, E, and the columns from 1 to 6, they correspond to the edges in the graph. We can see 1, 2, 3, 4, 5, 6. We have 6 edges. And if vertex A is connected to the edge 1, so we mark 1. It is connected to the it is also connected to the edge 2, so we mark 1 here. It's positive incident that they are connected. But as we can see, vertex A and is connected to edge 1 and edge 2, but it's not connected to edge 3, 4, 5, 6. So here A, 3, 4, 5, 6 stands zeros. Vertex B, it is connected to 3 edges, 2, 3, 5. So 2, 3, and 5 we have ones, and in all other places we have zeros. So vertex C is connected to the edges number 5 and 6, so we have zeros up to 5 and 6. And D and E, it's the same, similar to the previous vertices. Now we have adjacency matrix, and this matrix has vertices A, B, C, D, E both in rows, in columns and in rows. So if the vertex is vertex in rows is connected to vertex in columns, so then we have 1. So for example, vertex A is connected to vertex B and to vertex E. So as we can see, it is true, vertex A is connected to vertex B and to vertex E. But it is not connected to vertex D, to vertex C, and vertex A is not connected to vertex A. So if A was connected to A, so then we would have this edge around A. So you probably saw that in lectures. So, and again, B is connected to A, to C, and to E. So B is connected to A, to C, and to E. So and all the other vertices are, principle is the same for other vertices in the adjacency matrix. Now edge or incidence list, we have the set of vertices that are connected by edges. So A is connected to B. Yes, we can see that A is connected to B, A is connected to E, A is connected to E, B is connected to E. Yes. Now B is connected to C, C to D, and D to E. So also D is connected to E, and also E is connected to D, but we represent here as one edge because there's no there's no need for repeating these things. So we have 6 edges here, the number is 6, and we have 6 pairs here. So another one is adjacency list. So adjacent vertices are given for each vertex. So the adjacent vertices for A are B and E. For B, we have A, E, and C. A, C, and E. For C, we have B and D. So we have B and D for C. For D, we have C and E. And for E, we have A, B, and D. So everything is true. Now, search of the graphs in depth. So it's called depth first search, and abbreviation is DFS. So we begin from vertex. Here it is written 1, but we can call it V. Then we choose any adjacent vertex. Let's call it U. It can be this one. Here it is marked as 2, and this U is connected. U or 2 is connected to V or 1 here via an edge. So in this kind of search, we are going from vertex, in this case 1, to vertex 2. Then we go to vertex 4. This vertex 4 doesn't have adjacent vertices, so we are coming back to vertex number 2. And then for vertex number 2, we go to vertex 5. From vertex 5, we go to its neighbor 6. Then we go to its neighbor 3. From 3, we go to 7. And we see that we don't have any adjacent vertices to 7, so we go back to 3. And from 3, we go to 8. So here it is the representation on a bit different graph. So from 0 we go to 1, from 1 we go to 3, from 3 we go back to 1, from 1 we go back to 4, and now from 4 we go back to 1, to 0, and then from 0 we go to 2, then to 5, then back to 2, and then to 6. So we had to make this long come back from 4 to 0 and go to 2. So so a bit about the algorithm. So DFS is initiated from vertex A. Then vertex A is appended to the set called visited, and we go to, I will show you later how it is then in Python language. Then from vertex A we go to its neighbor B or C. In this case, let's take the alphabetical order and go to B. So DFS is performed with B. If it is unvisited, it is appended to visited set, and then we go to D or E. Let's take D, and DFS performed on D. since we can go deeper, there are no adjacent deeper vertices to D, so we come back to B and go to E. And then from E, as we form this huge comeback to C. So we have, so we will have, in the algorithm, we will have the set visited. That is important set to track the visited vertices. And here it is the algorithm, so we can see that we have the graph like this, and lines from 2 to 9, here they represents adjacency list. So this list is common in Python to use it. And now we have the set visited that I mentioned before. So here we track of visited nodes, and the function DFS, it operates on visited, on the set visited, on the graph itself, and on the node. Let's take initial node A, and if node is not visited, so it is printed. So printed, it means it is given in the output. So the output, you can see it is like the answer from all this algorithm. So the search is performed A, B, D, then E, F, and C. So if the node is not in visited set, so then it is added to visited, and then for each neighbor of that node, we are performing DFS. So until we go through all the graph. You can do your task of laboratory work with any software. It can be Python, it can be C#, it can be Java or anything. Just try maybe not to use the same algorithm as this. Be a bit more inventive, because it may be too easy, but this time I cannot. You are working alone, so without me in the beginning, so you may have this algorithm to that it would be easier for you in the beginning. Now, the breadth first search, it is the search performed in layers. So you can see it is depth first search in the example, and as a counter example, we have this breadth first search. So here it is performed some like in layers. So what I mean, it is 0, we take 0, then we go to 1 and 2, then we go to 3, 4, 5, 6. So the search is performed like this. And here we can see again that it is, we start from 0, then we go to the neighbors of 0, 11, 7, and 9. Then we go to neighbors of them 6, 3, 8, 10. Then we go to neighbors of these orange nodes, so 5, 4, 2, 12, 1. So search is performed like in layers. So what we have here, what we didn't have in depth first search. So we have here the queue, And so illustration of the queue. So because when BFS operates on D and E, so these are the child nodes of B. So the child nodes of C, which are F and G, they await. So that's why they stay in the queue. So if we have in the queue, we begin from A, we have A in the queue, then we print A and insert child nodes B and C in the queue. Then we print B and insert child nodes of B in the queue that are D and E. So C stays. Then we print C and insert its child nodes, so F and G. So we have 4 nodes here now. Then we print D and insert its child nodes, but as you can see that D doesn't have child nodes. So E doesn't have either, F doesn't have either, and G doesn't have either. So we just print those nodes and add nothing, and after this we finalize. So the answer is output A, B, C, D, E, F, G. So very simple output. And here we have the example in Python. So we have the it's very similar structure to depth first search, but here we have the queue, which makes things a bit harder, but the main idea is the same. And it's some may use this Python for programming and for completion of the task. So maybe I just will don't say more things to you, and you will do it yourself. So the task is, as you can find in the data sheet of laboratory work. So you need to draw a graph of 5 to 7 vertices. Choose one of graph visualization method and then write choose another visualization method and write a program to change the graph from one visualization method to another one, and write the program for depth first search and breadth first search, and that's it. So next time we will meet online during the time of your laboratory work. So I hope this will help for you